So this is actually a joint work with several brilliant minds. One is Matthew was my PhD, a postdoc at Berkeley from Paris 6. And then Airan was my student who is now doing a postdoc at Oxford. And Yufei Zhang was from Oxford as well, and now is an assistant professor at LSE. And I would like to, when I say some recent progress, more or less this continuous time reinforcement learning and regret analysis was almost non-existent until we started working on it. And the reason that we were looking at it was in Berkeley, it's a very, very active place where every student has to work on some sort of machine learning. And as a professor, so you're sort of being pushed to look into that problems. And coming from the control background, I was a little bit allergic initially with the term machine learning or reinforcement learning. And until I started looking at it, this is where the first part I'm going to talk about is any connection with reinforcement learning and control. And of course, we did some small pieces of work earlier, but then over the time, we realized that there's some really very close connection in reinforcement learning, which is wide open to the control community. And this is the central theme I'm going to present here. And I hope that we will generate sufficient interest for the control expert to come in. So we'll start with the problem formulation, and that is really starting from very basic examples, I would say, which is linear quadratic case, which is really the butter and bread for everybody in the control community. And then I slowly move in with all this linear quadratic case to show what are the ingredients that we need to work on, and then that allows us to move to the more general cases. And I wouldn't say the linear convex case that I'm going to present is really that general enough. But what is really interesting is from there, you see some very intimate connection of reinforcement learning with BSDE and so on and so forth. And also, it started pointing out new problems for us, which are more used to some classical concept of control. And here we need some new thinking about it. Okay, so I will have some brief discussion. So let's start with what is reinforcement learning. Reinforcement learning from a mathematical point of view is really control plus learning. Okay, and so if you actually think about what we do in control is we have a stochastic environment, and your objective is always trying to find an optimal control, or you study the associated value function. And you do existence, you study the regularity, and so on and so forth. Okay? And when you think about reinforcement learning is actually learn the environment while you're trying to find a control. So you have this added component of learning. And so if you think about chess and Go, and so reinforcement learning by and large, when from a CS perspective, has a lot of game component in it, because while you are learning, you view this stochastic environment as adversary, and you try to play against this unknown environment. Okay, so the very different fundamental difference between reinforcement learning and control are listed here, which is based on my understanding. Of course, it could be a lot of other differences. One is in reinforcement learning, there's this, one of the problems they study is called identifiability problem. So when you have a control, you have a system, you know all the parameters. We give a linear quadratic, we have all the parameters associated with it. We give a cost function, we have all the value function, all the objective function written ahead of us. And then we try to find the policy. And here, you're in the black box, you're trying to learn to find the optimal policy. Okay, you try to find the best strategy to win a game. But then, you learn how to play the game optimally. The question now is, when you learn this, can you go back to see why it's optimal? Meaning, can you actually identify this control with respect to the same parameter of the system? Okay, could there be different parameters of the system? So this is what we call the identifiability problem. And the other one, I think this is very interesting from us, is when you design a learning algorithm, what they do is, I see what I'm given now at a certain time and a certain state, and then design an algorithm which is a function of the time and the state. And so it's natural feedback form. Okay? In general, you would want to see that when I have a control feedback form, what the optimal policy or whatever the control policy I'm designing, how robust it is. And the robustness here is not necessarily to this state you're looking at, and very often is related to the system parameters. We don't do that very often in control. Okay, and then I think the last one, which is really right open to our community, is what I call the regret analysis. This is very fundamental because you don't know the underlying system, you don't know the parameter, you sort of manage to get an A in your exam, but you don't really know why you got an A, the parameter of the exam. And now, when you actually, sometimes you don't get to the optimal one, but then you take a step back. You say that if I can give him multiple chances, imagine Google is designing a robot. Okay, I have to be very careful that when I'm learning and trying to find the optimal strategy, I don't make tremendous or mistakes that is too fatal. Of course, I can learn quickly by taking a sharp turn so that I learn my system, but then I might kill someone. Okay, so I have to, if I'm giving 2 chances, or if I give M chances, where in learning is called episode, and we can think of this M chances, then how you try to find the best strategy to achieve some optimality or some close to optimality with reasonable cost. So this is what is the thing I'm going to talk about, and this regret analysis is going to be much clearer when I actually give a very simple formulation. So what is this? So you have, what is this? Okay, good. So you start with this very familiar thing. Well, you look at this, I have a dynamics and have a control parameter here, and this is even very linear, okay? Everything is linear. And then I put this, jump part just to get it more general. But you can focus on this part, that's a Brownian motion, that is with the drift control, with the linear with respect to the parameter. And of course, when you think about this linear one, I have parameter A star, B star. That's going to be used throughout this talk. And if I have this, in general, our control is saying, I give you an objective function. You try to find the control so that you try to minimize, in this case, as a cost of the running cost and the terminal cost. This is so familiar for us. And the only switch here is I don't know A star and B star. Okay? So in the parameter that I'm looking at, the parameters in the system A star and B star are now unknown. Okay? And when I actually have unknown, then it's going to be sometimes difficult for me to really optimize this anymore because I don't know the system. Well, I can take it back and say, well, the goal is if I don't know the system, I try to still take some controls to minimize some cost functionals that I'm going to define, which is not necessarily the previous one, which is I know if I know everything, that's my optimal value, but some cost functionals that make me keep us close to that one. Okay, So, special cases. Okay, we always start with the problem that we know the least. So if I actually have a linear quadratic case, okay, but suppose in the case that I do know this, okay, then of course this is, I take the linear quadratic, I take this f as a quadratic form, and the determinant is also quadratic, and then I assume everything that to my favor, make sure that they're all positive semi-definite and so on and so forth, that I can really utilize what a known knowledge here. Then what is this? We know a lot of this from the linear quadratic system. When I do have the known parameter, of course, one of the things that the first year student doing control will be learning this, that you know that this control is going to be in terms of these solutions which solve the Riccati equation. Really our butter and bread, okay? And of course, if you pay attention to this, this is where the key thing is. You pay attention to this Riccati equation, which we took for granted is this Riccati equation, the solution, which is the parameter here, PT, which is very critical for us to design a control policy, is parameterized by the star, A star and B star, which is the system parameter. Okay, so your optimal control, of course, is dependent on the system you're given, and in this case, I call it a parameter theta star, which represents the A and B. So this is what we know. Now, how do I actually put it into this system when I don't know A star and B star? Okay, I'm going to use this, the little toy I have in my hand. I twist it a little bit. I'm going to formulate a linear quadratic reinforcement learning in this regret case. And then I look at all the little recipes when I do the analysis that what I can do to study this and achieve what I want. Then I push it to the cases of more general one. Okay? And you can see the more general one is nothing but from quadratic to convex, and we are not able to do more than that at this moment. And for machine learning community, this is very important why regret analysis is. As I said, when I design the algorithm, they need to know that even if I don't know the system, how many error trial I can be confident to learn and then to get something close enough to what otherwise would be optimal. And the sample complexity and performance analysis is the criteria for them to design an algorithm. And in the meantime, I also keep in mind that I'm doing continuous time, and in the general machine learning community, they were doing discretization. Instead of doing the continuous time linear quadratic, they have this ODE algebraic equation for the Riccati equation, which is sitting on the discrete time grid. And really, we want to also, just from a numerical perspective, to study also the validation of whenever we study control problem, that's our usual practice, the validation and impact of the discretization. So this is more like a corollary, but the center is this linear quadratic. Okay. So how do we define it? Now, keep in mind I have the quadratic linear quadratic case, and with the A star B star, which I just say this is theta star as the system parameter, is unknown. And I also say that whenever I have a control, I could, for this particular case, linear quadratic, we know the optimal control. But suppose that in many cases when we actually don't know, we just apply any control, and I call this as a diffusion, control diffusion parameterized by alpha. And so how do I define this? This is the one page that one pay attention is usually when you actually are given in the machine learning, you give m chances. I give you m chances. Think about the exam. You have 3 times. You pass or not pass. You have m chances, and you don't know the A star, B star. But the system doesn't change much. The A star and B star doesn't change just because you don't know it. So you could be silly to exercise some control. okay? And when you actually exercise your control, let's say it's feedback, that's what when you're trying to learn, you apply the feedback type into the system with the A star, B star, even though you don't know. The system is there, I don't apply the optimal one, I just push it. Then what I get a response, right? I get a trajectory. It allows me to observe what is the responses. So this is what I get. I will get a response. And then I can try, so each of the episodes, this is basically each of the trial, I do get cause functional associated with it, okay? Now, what is the criteria here? Is if I apply some silly control here, I have some payoff I then collect, but then there was a difference of my payoff versus the optimal one. Yes?
I mean, I'm not so sure you can compute the expectation, you get a path, no? Right?
Yeah, depends on if you observe on discrete or you actually just observed a trajectory when you actually apply control.
But how do I compute the regret now if I don't know the parameters?
Great. Exactly, that's what my next sentence. So you look at this regret, you say, how is it possible? I don't even know this, right? And I can probably do this, but I apply anything and I don't know this. How can I actually do this one? Yeah. So this is exactly where we have to jump out of our control box. Okay? We are so precise. We want to know this so that we can compute. And the idea here, when we do regret analysis, is not going to be in terms of this. Instead, it's going to be looking at the difference of this. I don't know the one, but I can use, at least theoretically, and analyze this summation in terms of the episode scale. How is it possible? Okay, I'm going to show you. Okay, so basically, this is exactly, if you think about this phi I and this is phi star, and you think about this as a value function, what you're really looking at is the sensitivity or the robustness or what we call the Lipschitz stability of this control versus this control and the value function. So we are using control to say regularity, right? Value function and then the state. And I look at the value function or Lipschitz continuous or higher order regularity. But here, I need to actually study the payoff of this in terms of the regularity of the control policy. How sensitive I am. So maybe I should do this. This is my control for each of the episode. I don't know this one. Okay? But I have, say, of this. I don't know any of this. But my goal is actually to try to understand some kind of distance of this. And of course, this one I don't know either, because I don't know. So then my next step is say, I look at the Lipschitz continuity of the control policy, which is feedback, in terms of the parameter. My silly parameter versus the optimal parameter. Okay? And my goal is, after doing this I equal to 1 to m, my goal, in general, is to look at some scale of it in terms of either this or log m. So this is what regret analysis is. I give you so many chances. And whether you are able to achieve some bound, error bound, in terms of the chances. Of course, these all are going to be functions of the parameters of the underlying system. O in terms of Yeah, so I need to, in terms of this parameter of this scale, Okay, I just don't want to, when I actually have the learning things, that the whole learning error is going to explode. Okay? Yes?
When you go from constant C to constant C prime, if we are sitting in the linear quadratic case,
yeah,
the phi star is, the phi also is a linear function of x.
Yeah.
So there is no C prime, right? Because x is the range is.
We will see. Yeah, so if you just naively do, you're going to have linear regret. Okay? And the thing that we are trying to do and push the envelope here is actually, for the first time, you can actually achieve log regret. How you design algorithm.
What I mean is that in the difference phi minus phi star,
yeah,
is a constant multiplying by x.
Let's.
So there is a norm on x, and x is on the ring line, unbounded, right?
Let's wait till I show you the analysis. Okay, you will see. So this is, of course, the idea. Okay, and the idea is, as I said, I don't know the system. I have a Bayesian approach. I start with some estimate of the parameter. Okay, and the reason I choose the linear quadratic, just as Nizar was saying, because I know everything. I know the Riccati equation. What I would do is I pretend this parameter is what I use, and I use this parameter to replace the true parameter star in the Riccati equation. Okay, now I get some control, but it's not optimal, right? And then I let the system run. I do the trial. And then I collect all these samples. Now, when I have more samples, now I know a little bit more of the system. Okay? Then I can use this least square, general least square, to update my parameter. And then I continue of this. Okay? Of course, you can see that you have to be careful. How do you actually learn this parameter? So initially, you know very little, and you collect samples. You should not waste your chances. You should actually collect less samples and do less trial. As you learn the system better and better, you have more confidence. You're going to collect more trials so that you're best utilizing the parameters. Okay? So the design of this ML, how you divide these chances of M, is critical here, of course, to make sure you get the lower bound. So let's do this. So now, as I said before, I have to say, if I start with some naive sequence of this parameter trial, I have to have parameter bound here. Okay? And Nizar is going to like it because you didn't realize we use some techniques here from your paper. This parameter bound of theta L is going to be the first starting point. And then we're going to study the robustness of the control, which is linear in that case, and then try to estimate it. Of course, this is a recipe not just for linear quadratic, but I want to test run on the linear quadratics to see where the bumpy roads are. And then I can use this error bound of the parameter to this Lipschitz continuity of this feedback control, all the way drag it to this values estimation. Okay? So the first bound, and I should show you maybe the result here. What you do, suppose your system is good enough. Forget about this initial condition. This is basically ensure that your optimal control is not going to just visit part of the state so that you actually never see the real one. Okay, if the system does not degenerate, then you can actually manipulate, as I said, that when you take, so this is with high probability. I give you high probability. So there's a probability with high probability, which is parameterized by this pi, star, and delta, which I will choose accordingly of how to start the first trial, and then how to start the subsequent trial. And then I ensure that all my total summation of trial of this L is going to be less than M, then I can say that I can achieve the regret bound here that is going to be in log term of the M. So in the sense that I give you the 10 episode, your error function is not going to explode and it's going to be in a log term. Okay, yes?
Yeah, you just take the least square approximation of theta, estimation of theta?
Yeah, I'm going to do that. So this actually takes, to achieve this, I need the 3 steps, this, and this.
Yeah, but the theta parameter you're taking,
yeah.
Is it least square estimation or is it something taking randomly some confidence interval?
Oh, okay, so yeah, I'm going to show you how the estimation is done, the theta L. Yes. Yeah, how I choose that. Yeah. Okay. So the first one, I'm not going to do this. The first one is the parameter estimation. Okay. So I have this linear quadratic one. Okay. And if I knew this A star, B star, and if I observe everything, of course, I can write it just using martingale properties and the ethos. I can write it as expectation inverse of this ZT star that is my control, and then the trajectory, I can write it quite easily, okay? Now the problem is I don't know any of this, right? This is a very easy sampling idea, so then I try to take M samples, and then I replace the expectation by this average of that M samples. So this is a greedy algorithm, right? And then this is getting me the parameter theta hat. So this is how I estimate the parameter hat, okay? I don't know anything about the system, but I can mimic whatever you know the optimal thing. You do one step, I follow you. You do another step, I just follow, even though I don't have the key in my hand. And if I do this, then what I can show is the parameter. So of course, how do I actually estimate this to make sure that it's close to the optimal one? This is classical in machine learning concentration inequality, okay? And in this particular case, and the reason I wanted the linear quadratic is, in this particular case, this is all sub-Gaussian, and then when I do double integration, this is what Nizar did, is you do double integration, you ensure that you make sure all the things are going to be sub-exponential, okay? And if I have sub-exponential, then there's this Bernstein inequality that gave me the concentration inequality, okay? So that's exactly the thing. The analysis for the first step of parameter estimation is I take RID trajectories based on these silly controls, and I use this do the parameter estimation, copying the recipe from you, okay, which is optimal. And in order for me to estimate the error bound, I know that this is Gaussian, and I need to show this one is sub-exponential so that I can establish this concentration inequality. And I want to excuse me. Here. Oh, this is a control one. So, excuse me. The first part, if I'm able to show that these things after double integration is still sub-exponential with certain parameters, then I can easily use the Bernstein inequality to establish this concentration inequality. And of course, this is going to be double integration. Huh? This is double integration. Then I need the techniques borrowed from Nizar to actually show the things are still controlled. I can estimate the characteristic functions utilizing these techniques there. And then once I can show the sub-exponential, then I get the concentration inequality, and then I bound this error. Okay? The first step. Is that clear? Okay. Now, once I have the concentration inequality, you can see here that this bound is going to be bounded in the errors of your approximation, the accuracy you want to specify. But then this is going to be depends on these M choices for each of the episode. Okay? And once I have this, then I know how I massage my capital M, the episode, to ensure when I do the summation, this whole thing is still going to keep into the log scale. Okay? And this is the, and by the way, for people from machine learning, they're happy to see that, in fact, even if I do the discretization, the whole error is not going to explode. It's just going to add another term, which is in the term of 1 over n. 1 over n is the discretization grade. Okay? Now I have that. Now I need the second step of this one. I need to actually estimate the feedback control with respect to this. Okay? In order to do this, what I do is I heavily utilize this knowledge of linear quadratic. It has this Riccati equation, and what I do is I don't change the parameter of the system, but I can exercise my controls, and then in that sense, I can look at the corresponding Riccati equation now, replace the Riccati equation instead of the real system, A star, B star, by this new parameter I put in. And then I can characterize the stability in terms of the difference of that. So this is really Riccati equation. So when we actually, 3 years ago when we started this, it was shocking for us to see that in the CS community, they studied Riccati equation Lipschitz continuity in the discrete time, where they have the algebra equation. I would say, well, it probably should be somewhere in our community, because Riccati equation, we have been dealing with it for, how many years we know. And it turns out that we don't really have this Riccati equation stability in terms of parameter A star and B star. Okay, so we have to do it, but it's not that difficult. Okay, you can do that. And once you do that, then you move on to do a little bit, analysis. You can get to this, just as Frank is asking. The performance, even though I don't know the star, I can characterize it in terms of the distance of my parameter to this parameter star. And because I have a parameter star earlier with the concentration inequality, then I put everything back, I got the regret analysis. Okay, so this is basically the recipe. Any questions? Okay. Now, this is a toy model. How do we go to the linear convex one? Oh, 10 minutes, okay, thank you. I was just about. Okay, so for the linear convex one, of course, everything is the same, except in this case, I'm going to change the general payout functions to allow it to be convex or strong convex with respect to the controls, just to accommodate whatever learning community was doing, that they add the regularized the entropy and so on and so forth. I just need to ensure that this problem is well defined. And I do the same thing here, but then I have this puzzle. When I did earlier, I need very much the explicit Riccati equation that guide me to the road. In this case, what is my feedback control? I don't know, okay? We know that in control, we can establish the uniqueness of open loop control, okay? But then when we actually always go from open loop to the feedback loop, we use measurability, measure selection principle, or we use this compactification method, okay? But it's not sufficient for me to really go from here to here. I need this more parameterized. So this is where the BS forward-backward SDE comes in. And the other thing is, when I actually do this, I use the Nizar's techniques to estimate the sub-exponential, which I have the double integration, I have the Fubini for that version. But when I go to the more general one, I don't have it anymore. Okay? So we need the new inequalities and everything to do. So as we said, this is really different from what we were used to. And the recipe being, study instead of the stability of Riccati equation, we end up writing down the feedback control in terms of using maximal principle. You can write it in the forward-backward SDE. And then you can study the regularity, Lipschitz continuity of these controls in terms of the parameters. Okay, you need that. And then from the sub-exponential, we go to a more general class of sub-Weibull, which we benefit a lot from. Just now in the statistic community, for some reason, there's a huge study on this. So that allow us to leverage what our estimate is. And so for us to do this, I just want to put the assumption here to just make sure it's correct. So instead of having the general linear quadratic, the special linear quadratic, what I need is the running payoff function is going to be f0, 2 parts. The one part has to be convex and Lipschitz differentiable, meaning the derivative of it is Lipschitz continuous. And I also need this HA, which is usually, I think of this as a regularizers in machine learning. I want it to be good in the sense that it satisfies semi-continuous and convexity. Okay? So now, when I have this, I reproduce according to the recipe, except I have to redo all the analysis instead of relying on the Riccati equation. I can get the regret bound now because my knowledge is much less. I don't get the strong regret bound of log m. I got in the linear, sublinear one. Okay? And because my estimate here is much less here because I have a different class of random variables I have to deal with. And, okay, Haoyang is forcing me. Here, Haoyang, I need to deduct your PhD's thesis. Okay, so this is the one. And so I want to show this slide, how this, the feedback control in the general case is constructed from the forward-backward SDE. And you can see the form here. It's very familiar to us. You write it down as the usual Hamiltonian of the control problem, and you ensure that this part is also good in terms of exponential, sub-exponential property, and therefore you can consider this the x theta, y theta, z theta, m theta that actually are in the right place for the forward-backward. And now with this particular form, you can analyze these pairs in terms of these data parameters. So this is the stability of the forward-backward SDE in terms of parameters, okay, not in terms of the state. And then you establish the Weibull. I need to emphasize. In this case, you need a different norm to establish this one. The norm are going to be different. And once you have this, the concentration inequality will hold. How do I go back? Yeah, okay, I know. Oh. I got this. Okay, I think now I'm ready to stop. So by and large, in reinforcement learning, all these things are more or less irrelevant to us in many ways because it's not really control oriented. Instead, it's about designing algorithm and then try to show the convergence of the algorithm, okay? And the important thing for us is actually really taking a grip of this regret analysis and put it firmly in the domain of control, okay? And I hope that with the study, it's so simple, so easy to do that we will get more people interested in from this community to see this regret analysis, which is very critical and missing in this machine learning, especially reinforcement learning. And we do see several follow-up work already now in this domain, trying to study the different, slightly different settings in the regret analysis, and hopefully we will get there. And this is, if you're interested in seeing the analysis, this is a simple one that is in the Journal of Machine Learning Research, and this one that has is being revised for the SIME control for the linear convex case, which is doing this BSDE stuff. Okay, I think I'm going to stop here, and thank you very much.
So thanks for the speakers. Any more questions from the general audience?
So in the model, you assume at the beginning, you assume that A and B are unknown.
Sorry, I can't hear.
Yeah, sorry. That in the model, you assume that A and B, the parameters of the environment, are unknown, but the parameters of the reward, they are known. So you put them into all your solution of the linear quadratic problem. Is that realistic? Would it make sense to put Q
No,
and R?
we didn't assume that we know. We just say, if I knew this, then I would have a Riccati equation, right?
Yeah,
but I
right.
don't really know. What I do is I actually measure the distance of the potential node without knowing that one. I measure the distance to that one.
Oh, all right.
So I look at, this is the key. I look at this one without knowing this, but I don't really need to know. I need to know this bound,
Yeah,
the distance to
but
that.
in order to calculate V of phi,
Yeah.
Q and R, they are known.
This I don't assume this no.
No, but V of phi, so the other one.
No, I don't assume I know. I assume what I eventually get is this is what I can test. I can see how far away I am to the real one, which I don't know, in terms of this, by analysis of this, in terms of the episode number. So that's why I have to go through all this analysis without knowing all this. But the reason I use a quadratic one is to show you the recipe, what are the key things, how I go from here to here. But then in the convex case, I have to redesign the whole thing, but I know where to hit my target. Does that make sense?
Yes. Yeah,
okay. Thank you. It's a good,
Very much.
important clarification, yeah. Yeah, Yuri. Yeah.
Thanks for your talk. It was really interesting. I have a question about the way you pass to the linear term in theta. You use the inversion formula, which is essentially a least square that you referred to from Nizar. Have you looked at the nonlinear dynamics case where this correspondence between suboptimality in the values and suboptimalities of theta will break down? For example, if you have a nonlinear least square like a logistic regression?
We didn't do it because when we actually look at this recipe, that's a very good question. So one of the questions for us is we rely on this, very naive least square, right? And then you can go up and down and so on. Is any other thing? The thing is we don't know what to look for so that we can. And then we have the linear quadratic case, which we do know what to aim, right? And then when we just say, let's push a little bit to convex case, we already spend a lot of time dealing with this forward-backward SDE, where we have to do the stability analysis of that with respect to the parameter. And at the end of it, we said, okay, maybe take a break. But yeah, what are the parameters that can deal with nonlinear dynamics and whether that can be done? This is what I hope this community can actually get in. Yeah, it's just a very baby start. Yeah, thank you.
Any more questions? Okay.
Thank you. So I have several questions. One question is very simple about the terminology. So I am not an expert in general in reinforced learning, but it resembles strongly what was in old times as adaptive control. So this is the first question.
Yeah.
The second question, probably related, is there are some other settings. This setting is offline, but there is also online learning, which is adaptive control, if you want, which is more interesting. So it is like bandit problem.
Yeah.
So with, say, bias control, you need simultaneously estimate parameters and get the maximal reward.
Yeah.
So could you comment on this?
Yeah, so thank you. You're saying you don't know reinforcement learning. You actually asked a lot of this literature. So it's true when you actually look at, for example, do I have Duncan's thing somewhere? Duncan has done some work, okay, in these 80s about linear quadratic case, actually. And what they do is exactly in the domain of adaptive control. So for us, reinforcement learning from a control perspective was adaptive control. So in that case, what they have done was I look at the parameters, and then I try to discretize the system, and I try to say take an average of the system control, and I look at the error, and I try to show that I do this, eventually my control is going to asymptotically approach the optimal control. That's the control perspective. In this case, the objective is different. Here I wanted to say that I don't know anything, but I want to bound my regret. So the objective is different. And then in terms of, this is the offline, and then in terms of online, then there's a bandit setting. So reinforcement learning bandit is a very active field now, okay? However, the reinforcement regret analysis, which is actually so close to us, if you see the analysis, nobody has done that. And I think this is an opportunity that we can actually move in. Yeah, that's why. Thank you.
Okay, thank you. For the sake of time, maybe I'll leave one question for the Zoom participant.
Okay.
For a participant online, please, if you have any question, please feel free to unmute yourself. Anyone?
I don't see.
I would like to ask a question.
Sure.
May
I? Go ahead, please.
Do you see who is online? I don't see. Oh, sorry.
Doesn't matter. Okay.
Okay. There.
Can I stop sharing? No. Okay.
Doesn't matter.
Okay.
Doesn't matter.
Yeah, you can. Yeah, please ask your question.
Okay, my name is Wolfgang Rungadil. My question, thank you for the exposition, and my question is related a little bit to URIS. So in traditional stochastic control on the partial information, it is known that you lose optimality if you just first estimate the unknown quantities and then you replace the unknown quantities with their estimates. except in certain cases, and one of these cases is linear quadratic control. So you have this strict separation of estimation and control. Now, somehow you do a similar thing. You estimate and you control, but you don't do that completely separately. You do that hand in hand. And the objective is not to get a full convergence, but you simply want to bound this regret. Now, my question is, in the cases when you get a strict separation of estimation and control, this bound on the regret should theoretically go to 0. And my question is, would that go to 0 also in cases beyond the linear quadratic? With traditional techniques, it's very difficult to see whether a separation, a strict separation holds in cases beyond the linear quadratic. But maybe in your case, yeah, you could look at situations where this regret goes indeed to 0, and so you have a convergence of estimation control. I'm not sure whether I'm right, but the question was clear enough.
Yeah, very good question. So if we actually do know a little bit of the system where we can get a better estimation, so that's what the classical control has been doing. There's a asymptotic analysis by Duncan and the group where they do the linear quadratic, where they do show that the optimal control, once you do this learning or this adaptive control, they eventually, if you take, say, ergodic settings, then the error goes to 0. Okay, that's true. But in this case, if you look at the regret, you don't know anything about it, and you're taking a finite time horizon, and you're going to give only m. I'm not sure you will really have this regret of 0 unless you have additional information about the parameter. But it's a very interesting question that we should definitely think about it and see what additional thing could push us to actually reduce the regret. Right now, what we actually see, and also even in the discrete time, in this general, so we were trying to be aligned with the general machine learning. What they're doing is, even in the discrete time, the regret bound, the best of it is log. And they actually didn't expect us to get sublinear for the convex case. So, but with additional thing, there's a hope that we can actually reduce the regret. Yeah, thank you.
Thank you.
Let's maybe take one last question, maybe from the online group. Okay. Any more questions? If no, then let's thank the speaker again. And
thank you.